All right, so the last unit that we're reviewing here is the fluids. And remember, the whole idea around this is that when you're in a fluid and you're surrounded by these water molecules or even air molecules when you're just in normal air, it's caused by the little particles hitting you because they're constantly moving everywhere around. They're constantly colliding and they have energy and they're moving around. That's what causes temperature, by the way, but we won't get into thermodynamics. But they're hitting you, and that buoyant, and there's like a net force that's happening because all the particles are hitting you on all sides. Now, when an object is displaced in water, that creates a buoyant force. The buoyant force is the net result of all those forces, all those molecules adding up with each other. Why is there a force? Because whenever they hit you, they have a change in momentum. And any change in momentum is due to a force, right? So if a particle hits me and bounces the other way, I must have exerted a normal force to cause that molecule to bounce away, and an equal and opposite force was acting on my body too, right? By Newton's third law. So buoyant force is a new force we draw in our free body diagram. It's the net force. Whenever you're submerged in a fluid, and even in the air, all right, air has less density overall, but there's a buoyant force from the air. That's how hot air balloons work. That's why helium balloons can float in the air. There is a buoyant force that is acting. It always points upwards. That's the rule for the free body diagram. So we're going to be introducing this new force into our free body diagram. Buoyant force always points up. Is equal to rho vg. Now be careful on this one. V is the volume of the displaced water, which that may or may not be the same thing as the volume of the object itself. Like for example, when a boat is floating on the ocean, okay, the buoyant force is just the amount of the boat, the volume of the boat that's within the water. It's not the entire boat. Okay, the buoyant force, at least from the water, is only the volume that's being displaced in there. So be careful that you don't use the volume of the object necessarily, unless it's fully submerged. If it's fully submerged, then the buoyant force is the entire volume of the object. We define a new quantity we call pressure because the force is acting at all sides at any given moment in every location. There's a pressure. It's the force per unit area. And we have this static pressure equation, which we had derived in the lessons, but it comes from the fact that the deeper you go, the greater the force is. It's what causes the buoyant force. Ultimately, is that as you get deeper, the pressure increases. So this is almost like gravitational potential energy, rho gh. It's mass and density instead of mass. But it has to do with the fact that h is the vertical distance between 2 points. So when you do the static pressure equation, it's 2 points. We think about the difference between those 2 points. And just as a note fact, any amount of pressure greater than 1 atmosphere or 10 to the 5th pascals, that's the air pressure, normal air pressure, is called the gauge pressure. Okay, so sometimes we calibrate it relative to the normal pressure you experience every day on Earth. Bernoulli's equation is when we start using fluid dynamics. So everything up here was on fluid statics. That is, the fluids were not moving, everything's sitting still. But now we talk about dynamics when water is actually flowing. That's when we use Bernoulli's equation. Okay, dynamic and not static. The core principle here on this thing is water or work and change in energy or conservation of energy. You can look at the lessons for the derivation of that, but work is the change in energy. That's where that comes from. And the continuity equation is used is another equation we use. It's kind of like the conservation of mass, but we say that if the velocity of the water will change if the area changes. That's because water has to continuously be moving. We assume it's incompressible for simplified fluids. The Bernoulli's equation is again similar to the static pressure equation. Actually, it becomes the static pressure equation if the velocity is 0, but it looks like kind of energy terms, except density instead of mass, but this looks like kinetic energy, gravitational potential energy, and the pressure is kind of like the work part of the work and change in energy. But it's like conservation of energy in the sense that you pick 2 points and you're going to compute the pressure. All of these refer to the location at 1 point. All of this refers to the fluid location at a 2nd point, and you set them equal to each other like that. Okay, so let's go through some problems here. So we have a small rock sits at the bottom of a cup filled with water. The upward force exerted by the water on the rock is F0. So that's the buoyant force. The water is then poured out and replaced with the oil that's 3/4 as dense as the water, and the rock again sits at the bottom of the cup completely under the oil. Which of the following expressions correctly represents the magnitude of the upward force exerted? So this is just the F0 is the buoyant force. It's rho Vg. Now what's happening here is same volume because it's completely submerged, same G because we're on the same planet, but we're taking that rho and we're multiplying it by 3/4 because it's the 3/4 as dense as water. So we're multiplying the density by 3/4, and so there would be multiplying the force by 3/4 as well, and so that's going to be 3/4 F0. Okay. This one it cannot be determined without knowing the rock's volume. It's the same. It doesn't matter. It's the same volume in both cases because it's the volume being displaced. So even though we don't know the rock's volume, we do know that like it's the same in both scenarios. Okay, here we have a fluid flowing through two sections of cylindrical pipes as shown in the figure. The narrow section of the pipe is a radius r. The wide section is a radius 2r. What is the ratio of the fluid speed in the wide section to the narrow section? So whenever we change diameters or change areas, we always want to think about like, oh, we want to use continuity equation. That's going to be A1 V1 equals A2 V2, where A is the cross-sectional areas. Now over in the narrow section, the area is going to be pi r squared, the area of a circle, times the V in the narrow section is equal to the area over here, which is pi times 2r squared, times it in the wide section. You can divide the pi's, those cancel. This would be r squared times v narrow is going to equal 4r squared v wide. I'll just use w and n instead of writing it out. And we want the wide over the narrow, so we're going to divide that over here. Cancel that out. R squareds will cancel. Move the 4 over. You get 1/4 is equal to VW over Vn. So it's going to be 1/4 or A. So that makes sense. It's going to go slower. Remember, when it gets bigger, then the water doesn't need to flow as. You can see this in rivers and waterfalls and things like that. When the area narrows, the water is going to move faster, and then when it widens, the water looks like it moves slower. Okay, let's look at some FRQ problems. So we have a cylindrical object of height h. This would be a capital H. Yeah, this should have been a capital H. My bad on the picture. And the cross-sectional area A is fully submerged in a vertical fluid of density rho. So the density of the fluid is rho at a depth d below the surface. So this is the distance d. The object is uniform density rho naught and tethered to the bottom of the container with a light vertical spring of a spring constant k. Assume all parts of the problem that rho 0 is less than rho. So the density, this object has a density rho naught, and that density is less than there, right? So ultimately, because it's less dense, it is ultimately going to float. That's the way you want to think about it, because ultimately the mass of this thing is going to be less than the mass of the water in that same spot. So the buoyant force is going to be greater. But we'll do the math to show you that. Suppose the density of the fluid is increased while keeping the object's density rho 0, height h, and spring constant the same. Will the extension or compression of the spring increase? So first of all, it's an extension. Let's look at our free body diagram. Let's just draw our free body diagram. Because when you have something like this, and I'm asking you about the spring force or extension, and we're having it sitting here, we want to draw a free body diagram. So we have gravity, mg. Okay. Then we look at what's touching it. We have a buoyant force from the fluid pointing up. And then the spring, because I said the buoyant force is going to be greater than this thing, because this mg is going to be rho naught vg, and this buoyant force is going to be rho vg. How do I know rho naught versus rho? Because the mass of the object is the density of the object times its volume, and the buoyant force is the density of the liquid that we're surrounding it. So rho is the water that we're in. That's why the buoyant force is related to the density of the liquid. The mass of the object is related to the density of the object itself. All right, which is rho naught, okay? And because rho is greater than rho naught, this force is greater. That means because the acceleration is 0, right? That means the spring, in order to keep it from floating upwards, the spring is exerting a downward force, right? In order to keep it in motion. Now, what happens is if we increase the density, what's going to happen is this force is going to increase, right? Because we're going to increase the rho. We're keeping all this stuff the same. So in order to compensate for that bigger upward force, the spring is going to have to pull even harder, so it's going to need to stretch more. Because remember, spring force is related to how much you stretch it. So the spring force also has to go up, and so that is going to increase. So the explanation we're going to say here is because, so increasing rho increases the buoyant force. which requires the spring to pull down more to keep the cylinder from floating away. Thus, the spring must stretch more. Okay, so now we want to derive an equation for the extension of the spring in terms of rho naught g, h, and k using the buoyant force and height. Okay, using I should just told you just to derive it. Okay, so this one here, we just say the upward force is equal to downward forces, right? Because the net force is 0. So rho vg is going to equal rho naught vg plus the spring force, which is kx. So then we can just solve for x here, right? So this is the upward force, has to equal the downward force because the acceleration is 0, right? It's our free body diagram process, our forces process. So rho vg minus rho naught vg is equal to kx. You just divide that by k, and that's what you get your expression here. Okay. If the cross-sectional area of the object increases, how would the spring's extension change? Okay, so that means if we increase the cross-sectional area and did not change anything else about the object, right? Then how is this going to actually? Are we supposed to do it? Oh, we're not given the volume, so we need to throw in the volume here. Sorry about that, because they weren't given the volume. So here, okay, so let's just take one more stab at that. So the volume of the object is going to be the volume of the cylinder. So we can the V. So let's make this first Vg times rho minus rho naught over K. And the volume is pi r squared, or it's actually just the area times the height. AHG rho minus rho naught over K is equal to X. All right, so now in this part, when we're asking if the cross-sectional area increases, so this part increases, everything else stays the same, then it's going to increase. So increasing A in our derivation in part B would cause X to increase. So we just want to connect that and make sure that we understand from our derivation, A goes up, the X will increase. Okay, let's look at another one here. So tank Y is a large tank with air open to the top as shown in figure 2. The bottom of tank Y is connected to a short horizontal pipe of radius R. So this is a radius R with a closed valve. Tank Y is filled to a height h0 above the horizontal pipe. Tank Y is specifically designed so that when the valve is open, the surface of the water moves downward at a constant speed Vs. So the water is going to move at Vs. At time t equals 0, the valve is open, so water is going to come out here, and this is open to the air. So this is atmospheric pressure here. And now that we've opened this valve, this is also atmospheric pressure. Derive a relationship between this speed Vp at which the water exits the pipe and the changing height of the surface to show that Vp is equal to Vs squared plus 2gh. So how are we going to relate the velocity from here to here? There's two things that we're going to ultimately look at. We're going to look at continuity equation and Bernoulli, because it's dynamics, right? So we're going to look at continuity equation, we're going to look at Bernoulli's equation. So let's take a look at first continuity equation. Well, we don't know the area. We know the area of this guy, but we don't know the area of this thing. So that's going to make it really hard. Like, we do know the velocity here is Vs, but we're trying to derive this velocity, and I know this area, but I don't know this area. So ultimately, like, I don't really know, like, this isn't going to really help me at this point. So let's look at Bernoulli's equation. Rho gh1 plus 1/2 rho v1 squared is equal to p2 plus rho gh2 plus 1/2 rho v2 squared. Okay, so now when we do something like this, what we want to think about is, okay, what is our reference height? So this is where it is h equals 0. We also want to think about our 2 points, right? Point here, that will be 1, and point here, that will be 2. Now, they both have the same pressure at those points, so we can cancel those because they're both going to be the same. They're both open to the air, so they're atmospheric pressure. This guy down here, for 2, his height is 0, right? Because we make that h equals 0. So then it's just looking at this equation. It's rho g times the height at 1, which is h0, plus 1/2 rho, and then the velocity here is vs squared, is equal to 1/2 rho times the velocity here, which is vp squared. Notice that the rho's will cancel when we divide that out. So we're going to multiply by 2. We get 2gh0 plus vs squared is equal to vp squared. And so therefore vp is going to be square root of 2gh0 plus vs squared, right? So derive a relationship between vp and the radius r of the top of the surface to show that vp equals it. So now that we know the velocity here and here, we can then do the continuity equation, right? So the top of the surface, this is going to be area. It's going to be pi r squared. V1 is going to be the vs. And then down here, it's going to be pi times little r squared. V2 is going to be vp here. So then the pi's cancel, and we just want to solve for the r here. So r squared is going to be little r squared vp over vs. That's little r squared. Actually, what do we want to solve for? We want to solve a relationship between vp. Oh, they just want to give us vp. Sorry, you wanted to show that part. So you want to solve for vp, actually. So vp is going to be big R squared vs over little r squared. And so that we finished that derivation there. Now, when the radius is sufficiently greater than r, vp can be approximated as this. Justify this claim. So this is like looking at your equation, is to say when the radius of the tank is sufficiently greater than r, vp can. Let's take a look at this one here. So when r, well, actually, let's take a look at, so when r is much greater than little r, then this is going to be really big. Then vp is going to be much greater than vs, right? So like, let me see how we're going to do this. We want to solve for vp, so we're going to talk about this thing. Yeah, so when, okay, so let's kind of reason out this way. If r is really, really big at r, it's not that vp is necessarily infinite. It's that so that implies vs is going to be very small, almost 0. Okay, because when this radius is big, it's not like this is going to shoot out necessarily infinite. It's just that this thing is going to shrink down to a like pretty small number. And so if you reason that into there, then that means vp is going to be approximately square root of 2gh0. Okay, like that. So that's kind of the justification we would use. We would say like, well, okay, so for large r, vs is very small, almost 0. So vp can be approximated as the square root of 2gh0, like that. Okay. Tank Z is a large tank whose top is open to the air and shaped as shown in figure 3. So now we're going to switch the shape of the tank. The bottom tank Z is connected to a short horizontal pipe with a closed valve. Tank Z is filled with water to a height h0 above the horizontal pipe. At time t equals 0, the valve of the tank is open. So again, we're opening this tank. Let's see. Yeah, h0. Does the speed at which the surface of the water move downward increase, decrease, or remain the same over time as the water exits the end? Justify your answer by using or referencing equations from both part bi and b2i. So either of these equations you can take a look at. So remember that what's going to happen here is as it gets lower, clearly the radius is good. So as the water decreases, water level decreases, the r is going to increase, right? So r is going to increase here. So if we look at our equation here, if r increases, okay, and if r is going to increase, then the vs is going to slow down, right? The vs is going to go down, assuming the vp is about the same, right? So, well, actually, I guess you don't necessarily assume that the vp is the same. So when the r increases, vp goes up, but the vs is going to kind of go down. So probably the easiest if you set them equal to each other, to be honest, right? So r squared over little r squared, because it's like, well, how's the vp going to change? But they're going to be the same, right? So that is going to equal square root of 2gh0 plus vs squared, right? So ultimately, like, you can divide. Well, we want to solve for vs, so I'm going to move this vs to the other side. So big R squared over little r squared is going to be square root 2gh0 plus vs squared divided by Vs squared. And so you can, I don't know, I moved it into the square root. So ultimately, when r is going to increase, right? When the radius increases, ultimately by continuity equation, you should see that the Vs is gonna have to go slow down. So what ends up happening is that the Vs is going to like if you want this whole quantity to go bigger, you can't increase both of these. Well, let's make it more like this. This is one way to justify it. Just divide the Vs squared to make this plus 1. So divide the Vs squared into each of them, like separate them out. Right? So if this is going to go up, then this denominator is going to have to go down, right? So this has to decrease. So it definitely decreases there. Probably the other way that's maybe a little simpler to justify this is to say that like almost use the continuity. They want to use both of them. So say that like the as the H0 decreases, like let's assume Vs is very small. As H0 decreases, the Vp has to go down, right? So the velocity of the water is going to go down. If Vp goes down, right, then as R increases, Vs has to go down also, right? So hopefully you kind of see that. So as it decreases, H0 is going to go down, which means the Vp goes down. And as Vp goes down and R increases, then the Vs also has to go down, like that, right? So that's kind of like that's the other line of reasoning you could also use. So as the water level decreases, you could say H0 decreases. So Vp decreases. And you can refer to the Vp equals square root of Vs squared plus 2 GH0. And then which means Vs decreases from the equation r squared over little r squared Vs is going to equal Vp. Because if Vp goes down and r goes up, which means Vs decreases as r increases, like that. Because r is going to increase, Vp is going to go down, so this thing definitely has to go down to compensate. Okay, so those are a couple ways to justify it, but that's kind of like the reasoning. You want to just refer to the equations and somehow and show that level of dependency. This one is a lot trickier, so I like picking that one to understand that dependency there.